Recent research has revealed that the winds on Mars are far stronger than previously believed. For decades, scientists thought they understood Martian wind patterns. Surface landers measured gentle breezes. Climate models predicted winds rarely exceeding 50 kilometers per hour. Mars, with its thin atmosphere, just 1% the density of Earth's, seemed incapable of generating powerful storms. We were wrong. By analyzing satellite images from the ExoMars Trace Gas Orbiter and Mars Express, scientists found that dust devils, those towering vortices of spinning dust, can reach speeds of up to 160 kilometers per hour. That's 44 meters per second. That's hurricane-force winds on a planet where the atmosphere is so thin you could barely feel a breeze. This discovery isn't just a footnote in atmospheric science textbooks. These findings fundamentally reshape our understanding of Martian weather, dust transport, and surface geology. They explain features we've observed for decades but couldn't account for. Migrating sand dunes, persistent dust layers suspended in the thin atmosphere, erosion patterns that seem to require catastrophic events. And critically, this discovery has direct consequences for mission planning and engineering. Every rover we send to Mars, every future habitat we design for astronauts, every solar panel array we deploy, all of them will face winds far more powerful than we anticipated. In this video, we'll break down what was discovered, why it matters scientifically, and how it will shape the future of Mars exploration. Let's get started. Before we dive into the groundbreaking discovery, we need to understand what dust devils are and why they're so important to Mars. What are dust devils? Dust devils are a well-known feature of Mars, and Earth, for that matter. These short-lived atmospheric vortices form when sunlight heats the ground unevenly, causing warm air to rise rapidly and spin. Here's how they form. Step 1. Surface heating. During the Martian day, sunlight strikes the surface. Dark rocks and soil absorb more heat than lighter-colored areas, creating temperature differences across the landscape. Step 2. Convection. The heated air near the surface becomes less dense and begins rising. This creates an upward flow, a thermal plume ascending through the cooler air above. Step 3. Rotation. Wind shear. Differences in wind speed or direction at different altitudes causes the rising column of air to begin spinning. Just like how figure skaters spin faster when they pull their arms in, the rotating column tightens and accelerates as it stretches upward. Step 4. Dust entrainment. The spinning vortex creates low pressure at its center. This pressure difference, combined with strong winds at the base, lifts fine dust particles from the surface. The dust becomes visible, revealing the otherwise invisible vortex. Step 5. Movement and dissipation. The dust devil moves across the landscape, driven by prevailing winds. It persists as long as surface heating continues and the atmospheric conditions remain favorable. Eventually, as the sun angle changes or the vortex encounters obstacles, it dissipates, dropping its dust cargo back to the surface. Dust devils on Mars versus Earth, Martian. Dust devils are far more common and often more spectacular than their terrestrial counterparts. On Earth, typical height 10 to 100 meters, occasionally up to 1 kilometer. Duration a few minutes. Wind speed 25 to 40 km/h typically. Frequency common in deserts, rare elsewhere. On Mars, typical height 101,000 meters. Some reach 8 kilometers, higher than Mount Everest. Duration minutes to hours. Wind speed previously thought to be 30-50 km/h maximum frequency. Extremely common during Martian spring and summer. The difference comes down to atmospheric dynamics. Mars has lower atmospheric pressure, easier for convection to develop, greater temperature extremes between day and night, no vegetation or water to dampen surface temperature variations, abundant fine dust particles ready to be lifted. Why they matter? Dust devils aren't just atmospheric curiosities. They're critical to understanding Mars for several reasons. 1. Dust lifting mechanism. Dust devils are one of the primary ways dust gets lifted from the Martian surface into the atmosphere. Once airborne, dust can remain suspended for weeks or months, affecting global climate. 2. Surface modification. As dust devils travel across the surface, they scour the ground, creating distinctive patterns called devil tracks, dark streaks where the vortex has removed lighter-colored dust to reveal darker soil beneath. 3. Power for rovers. One of the unexpected benefits of dust devils is that they can clean solar panels on Mars rovers. Spirit and Opportunity both experienced mysterious power boosts when dust devils passed over them, sweeping away accumulated dust and restoring solar panel efficiency. 4. Climate driver. The dust lofted by dust devils affects how Mars absorbs and reflects sunlight, influencing atmospheric temperatures, wind patterns, and even the development of global dust storms. For decades, scientists have studied dust devils using images from orbit and measurements from surface landers. We knew they existed. We knew they lifted dust. We could see their tracks across the Martian surface. What we didn't know, what nobody realized until recently, was just how powerful they really are. The discovery of Mars's true wind speeds wasn't the result of a single dramatic observation. It was the product of patient, systematic analysis of decades of data using cutting-edge artificial intelligence. The research team. The study was led by Valentin Bickel at the University of Bern in Switzerland, but it represented collaboration across multiple institutions and relied on data from 2 European Space Agency missions that have been orbiting Mars for years. The data sources. The research utilized images from 2 high-resolution camera systems. 1. CASIS, Color, and Stereo Surface Imaging System, mounted on the ExoMars Trace Gas Orbiter, launched in 2016, capable of capturing images at 4.5 meters per pixel resolution, can photograph the same area from different angles for stereo imaging. 2. HRSC, High-Resolution Stereo Camera. Mounted on Mars Express, orbiting since 2003, provides both wide area coverage and high-resolution targeted imaging, has captured over 50,000 images of the Martian surface over 2 decades. Together, these cameras have created the most comprehensive photographic record of Mars's surface ever assembled. But the sheer volume of data created a problem. How do you find and analyze dust devils in tens of thousands of images? The traditional approach. Historically, scientists identified dust devils by manually reviewing images, a time-consuming process that could only sample a tiny fraction of the available data. Researchers would look for the characteristic spiral shapes and shadows cast by dust columns. This approach had limitations, extremely labor-intensive, hundreds of hours per study. Subject to human bias, different researchers might identify features differently, could only analyze a small subset of available data, provided isolated snapshots rather than comprehensive statistics. The deep learning solution, Bickel's team took a radically different approach. Train an artificial intelligence system to automatically detect dust devils across the entire image archive. How it worked. Step 1. Training data. Researchers manually identified several thousand confirmed dust devils in images, marking their locations and characteristics. This became the training dataset. Step 2. Algorithm development. A convolutional neural network, a type of AI particularly good at recognizing patterns in images, was trained on this dataset. the algorithm learned to identify the visual signatures of dust devils, spiral patterns, characteristic shadows, textural features that distinguish dust columns from background terrain. Step 3. Automated detection. Once trained, the algorithm scanned through more than 50,000 high-resolution images, automatically flagging potential dust devils. The system could process in hours what would have taken human researchers years. Step 4. Verification. Human experts reviewed the algorithm's detections to filter out false positives and confirm genuine dust devils. The scale of analysis. The result was unprecedented, the most extensive analysis of dust devil activity ever conducted. The algorithm detected dust devils across multiple Martian years, diverse terrains, plains, craters, dune fields, volcanic regions, all seasons, different times of day, various atmospheric conditions. This provided the first global, long-term statistical view of dust devil behavior rather than isolated anecdotal snapshots. Selecting events for detailed study from the tens of thousands of detected dust devils, the team selected 300 events for detailed measurement. These were chosen because they appeared in multiple images, taken seconds or minutes apart. They showed clear, well-defined structures. Stereo imaging was available for precise three-dimensional analysis. Surface features near the dust devils could serve as reference points for motion tracking. For these 300 cases, the team could do something never done before: directly measure wind speed. Dust devils are visible, but wind is invisible. How do you measure the speed of something you can't see? The answer lies in tracking the motion of the dust itself and using the terrain below as a reference frame. Stereo imaging, seeing in 3 dimensions. The first challenge was determining the dust devil's precise location in 3-dimensional space. This is where stereo imaging becomes crucial. When you look at an object with 2 eyes, your brain combines the slightly different views from each eye to perceive depth. Stereo imaging uses the same principle. The process. 1. Multiple perspectives. The CASIS and HRSC cameras captured images of the same dust devil from different angles as the spacecraft orbited Mars. Because the camera's position changed between shots, each image showed the dust devil from a slightly different viewpoint. 2. Parallax calculation. By analyzing how the dust devil's position appeared to shift relative to background features, craters, rocks, dunes, the team could calculate its distance from the surface and its 3-dimensional structure. 3. Height and structure. This revealed not just where the dust devil was, but how tall it stood, how wide its base was, and the shape of the dust column. Time sequence, analysis, tracking motion. The second challenge was measuring how fast the dust devil was moving. This required images taken seconds or minutes apart. The process. 1. Image pairs. For each of the 300 selected dust devils, the team identified image pairs showing the same vortex at different moments in time. 2. Surface reference points. Using identifiable features on the Martian surface, distinct rocks, crater rims, dune edges, the team established fixed reference points. 3. Position tracking. By measuring where the dust devil appeared relative to these reference points in each image, they calculated how far it had traveled. 4. Speed calculation. Distance traveled divided by time elapsed equals speed. Simple in principle, but requiring extraordinary precision in execution. Measuring vortex dynamics. But the dust devil's travel speed, how fast it moves across the landscape, isn't the same as its internal wind speed, how fast the air is rotating within the vortex. To measure internal wind speeds, the team analyzed. 1. Dust particle motion. The movement of individual dust streamers within the vortex, tracked frame by frame. 2. Vortex rotation rate. How quickly the visible dust column completes a full rotation. 3. Column diameter. Combined with rotation rate, this reveals the tangential velocity of the rotating air. The surrounding wind field. Here's where the team made a crucial observation. The strongest winds weren't inside the vortex itself, but in the straight-line winds surrounding it. Think of a dust devil like a tornado, which it resembles, though the physics are different. The rotating column is the most visible part, but it's surrounded by a larger wind field, air being drawn inward toward the low-pressure center, accelerating as it approaches. By tracking dust movement both inside and outside the vortex, the team could map this entire wind field, revealing patterns previous studies had missed. Accounting for uncertainties. Every measurement has uncertainty. The team had to account for image resolution limits. Features smaller than 4 to 5 meters might not be distinguishable. Timing precision. Exact time between images isn't always known to the second. Atmospheric distortion. Mars's thin atmosphere can still slightly blur images. Dust devil variability. The vortex itself may be strengthening or weakening between images. Through careful statistical analysis, they quantified these uncertainties and ensured their measurements were robust. The result. After analyzing 300 dust devils with this methodology, the team had something unprecedented: direct, quantitative measurements of near-surface wind speeds on Mars, linked to visible atmospheric phenomena, covering diverse regions and conditions, and the numbers were shocking. The results of Valentin Bickel's study weren't just surprising, they were paradigm-shifting. The official findings: some dust devils on Mars generate wind speeds of up to 44 meters per second, which translates to 160 kilometers per hour or 99 miles per hour. To put that in perspective, Category 1, Hurricane 119, 153, km/h. Category 2, Hurricane 154, 177, km/h. Severe thunderstorm 90+, Willamette gale force winds 62-74 km/h. Mars's dust devils are producing winds approaching Category 2 hurricane strength. Why this is shocking: for decades, atmospheric models and surface measurements suggested Martian winds rarely exceeded 50 km/h, with maximum gusts perhaps reaching 70-80 km/h under extreme conditions. The new measurements show winds more than 3 times stronger than previously believed. This isn't a minor correction. It's a fundamental reassessment of Mars's atmospheric dynamics. How did we get it so wrong? The underestimation came from several factors. 1. Limited surface measurements. Mars landers and rovers measure wind speed at fixed locations. If a powerful dust devil doesn't pass directly over the weather station, it won't be recorded. The data was biased toward average conditions, not peak events. 2. Instrument limitations. Wind sensors on spacecraft like Curiosity have measurement ranges typically capped around 40 to 50 kph. Faster winds might exceed sensor limits or be filtered out as anomalous data. 3. Modeling assumptions. Climate models of Mars's thin atmosphere assumed that low atmospheric density would limit wind speeds. The physics suggested that without much air mass, winds couldn't generate significant force. This turned out to be incomplete. 4. Confirmation. Bias. Once the 50 km/h figure became accepted in the literature, subsequent research tended to confirm rather than challenge it. Scientists weren't looking for faster winds because they didn't expect to find them. The role of straight-line winds. Here's where Bickel's team made a crucial additional discovery. The strongest winds weren't confined to the spinning vortex cores. Surrounding each dust devil was a field of powerful straight-line winds, air being drawn toward the low-pressure center of the vortex. As air accelerates inward, It can reach velocities exceeding the rotational winds within the vortex itself. These straight-line winds played a critical role in lifting and sustaining dust. They scoured the surface, breaking loose dust particles, accelerated dust upward toward the vortex, created the distinctive devil tracks, dark streaks where dust had been removed, contributed to the overall wind field measured by the study. Previous research had focused primarily on the rotating column, missing this crucial component of the dust devil's wind system. Statistical significance. The 160 km/h figure represents the upper range of observed wind speeds. The full distribution shows median wind speeds, 70 to 90 km/h, still significantly higher than old models. Common peak speeds, 100-120 km/h maximum recorded, 160 km/h lower bound, 40-50 km/h, matching older estimates, but representing the weakest dust devils, not the average. This study provides the first global, long-term measurements of near-surface Martian wind speeds linked directly to visible dust activity. It establishes a firmer baseline for understanding energy flows in Mars's boundary layer, the lowest region of the atmosphere where most weather occurs. Not rare, but common. Perhaps the most important finding, these are not rare bursts of wind, but consistent, measurable forces. The data showed that powerful dust devils are common during Martian spring and summer, occurring thousands of times per day across the planet. This isn't a question of occasional extreme events. It's the normal state of Martian weather. The discovery of stronger-than-expected Martian winds solves several long-standing mysteries about the planet's surface geology. The dune migration problem. Mars is home to extensive dune fields, particularly in regions like Olympia Undae, vast dune seas near the North Polar Cap, Hellespontus Montes, complex dune systems in the southern highlands, Gale Crater, where the Curiosity rover has photographed active sand movement. For years, scientists observed that these dunes were migrating, slowly shifting position over months and years. But the calculated wind speeds from older models were barely sufficient to move sand grains. The physics of sand transport. Moving sand requires wind speeds above a threshold value determined by grain size, larger grains need stronger winds, atmospheric density, less dense air provides less force, surface friction, and cohesion. On Mars, with atmospheric density just 1% of Earth's, the old wind speed estimates suggested that sand transport should be rare and slow, requiring exceptional conditions. Yet the observations showed dunes migrating meters per year, active ripple fields constantly reshaping fresh slip faces on dunes indicating recent movement. The new explanation, with wind speeds regularly reaching 100-160 km/h, sand transport becomes not just possible, but expected. The stronger winds provide sufficient force to overcome surface friction even in Mars's thin atmosphere. We no longer need to invoke rare extreme events, like global dust storms, to explain dune migration. Consistent, seasonal dust devil activity is enough. Streak formations and devil tracks. Orbiting spacecraft have photographed thousands of dark streaks across the Martian surface. Tracks left by dust devils as they scour away lighter-colored dust to reveal darker soil beneath. These tracks appear and fade over weeks to months as dust devils create new streaks, dust settles back down, new dust covers old tracks. The density and pattern of these tracks provides a visible record of dust devil frequency and intensity. The new wind speed data helps explain how dust devils can create such clearly defined tracks, why some tracks are wider and more prominent than others. The seasonal variation in track formation, erosion and surface weathering. Stronger winds have implications for long-term geological processes. 1. Aeolian erosion. Wind-driven erosion shapes rock formations. Features like yardangs, streamlined ridges carved by wind. Ventifacts, rocks polished and faceted by wind-blown sand. Erosional valleys and channels. All of these form faster and more effectively with stronger winds. 2. Dust distribution. The patterns of dust coverage across Mars, why some regions are dustier than others, depend on wind dynamics. Stronger winds can transport dust farther and redistribute it more effectively. 3. Surface age estimates. Geologists estimate the age of Martian surfaces partly by counting impact craters. More craters, Saturn's older surface. But wind erosion can erase small craters. If winds are stronger than thought, erosion rates are higher, and age estimates may need revision. Explaining ancient features. Some Martian geological features appear to require more vigorous atmospheric activity than modern Mars can provide. These include large-scale aeolian formations dating back hundreds of millions of years, sedimentary deposits suggesting widespread dust transport, erosion patterns in ancient terrains. The stronger wind speeds help close the gap between what ancient Mars could do and what modern Mars can do, suggesting that even current Mars is more geologically active than previously believed. Martian dust isn't just a geological curiosity. It's central to the planet's climate system, and stronger winds fundamentally change how we understand that system. The role of dust in Martian climate dust affects nearly every aspect of Mars's atmospheric behavior. 1. Solar radiation. Dust particles suspended in the atmosphere absorb and scatter sunlight. More dust means less sunlight reaches the surface, cooling the ground. More sunlight is absorbed by the atmosphere, warming the air. This temperature redistribution drives wind and weather patterns. 2. Thermal inertia. Dust-covered surfaces heat up and cool down differently than clean rock or sand, affecting local temperature variations and convection patterns. 3. Atmospheric opacity. The amount of dust in the atmosphere determines how clear or hazy the Martian sky appears. During global dust storms, atmospheric opacity can increase dramatically, turning midday into twilight. 4. Storm development. Dust heating can strengthen atmospheric circulation, which lifts more dust, which causes more heating, a positive feedback loop that occasionally triggers planet-wide dust storms. The dust-lifting mystery. For decades, scientists struggled to explain how Mars maintains its background dust haze. Even outside major dust storms, there's always dust suspended in the atmosphere. But where does it come from? Previous models suggested dust lifting was relatively rare, requiring strong winds. Most dust came from a few active source regions. Background dust levels should decline without major storms to replenish them. But observations showed persistent thin layers of dust at various altitudes, remarkably stable atmospheric dust levels between storms. Dust present even during periods with no major storm activity. The resolution, stronger winds measured in this study, suggest that dust mobilization is more common and more effective than previously thought. If dust devils routinely generate 100–160 km/h winds, they're lifting dust constantly, not just during rare intense events. This provides a continuous source of airborne dust that explains the persistent haze. Suspended dust layers. Mars orbiters have detected thin layers of dust suspended at altitudes of 10 to 30 kilometers, far above where typical convection would lift them. These layers can persist for weeks or months. The stronger winds help explain this phenomenon. Dust devils reaching 8+ kilometers in height can inject dust directly into the mid-atmosphere. The powerful updrafts carry fine particles to altitudes where they remain suspended. Horizontal winds at those altitudes can then spread dust globally. Regional dust activity. Mars experiences regional dust storms, smaller than global events, but larger than local dust devils, throughout the Martian year. These storms often emerge from specific areas known as dust storm source regions. The new understanding of wind speeds suggests these regions aren't unique in their ability to lift dust. Rather, they're areas where meteorological conditions, temperature contrasts, topography, surface composition favor the formation of particularly intense or numerous dust devils. The stronger baseline wind speeds mean regional storms can develop more easily and persist longer. Implications for climate modeling. Every Mars climate model, used to predict weather, understand seasonal changes, and forecast dust storm development, includes parameters for how easily wind lifts dust from the surface. These parameters, called dust lifting efficiency or threshold friction velocity, were calibrated based on the old wind speed estimates. With the new data, models need to be recalibrated with higher wind speeds. Dust lifting efficiency is likely higher than current models assume. Predictions of dust storm timing, intensity, and duration may need revision. Our understanding of how Mars's climate has evolved over millions of years requires updating. The feedback loop. Stronger winds create a more dynamic dust cycle. More wind, more dust lifted, more atmospheric heating, stronger circulation, even more wind. This positive feedback helps explain why Mars, despite having such a thin atmosphere, can generate planet-wide dust storms that last for months. The atmosphere may be thin, but it's powerful and reactive. The discovery of stronger Martian winds has profound implications for every robotic mission we've sent to Mars, and every future mission we're planning. The dual nature of wind. For solar-powered Mars rovers, wind is both blessing and curse. The blessing. Solar panel cleaning. Mars is a dusty planet. Over time, fine dust settles on solar panels, reducing their efficiency. On Earth, rain would wash panels clean. On Mars, there's no rain, but there are dust devils. Spirit and Opportunity. NASA's twin rovers. Spirit and Opportunity, which landed in 2004, were designed for 90-day missions. Both survived for years, partly thanks to unexpected cleaning events. Periodically, their power output would suddenly spike, sometimes increasing by 5 to 10% overnight. Images would show noticeably cleaner solar panels. The cause? Dust devils passing directly over the rovers, their winds scouring away accumulated dust. These cleaning events extended both missions significantly. Spirit operated for 6 years, designed for 90 days. Opportunity operated for nearly 15 years. Both rovers would have failed much sooner, without dust devils clearing their panels. The curse, erosion, and wear. But the same winds that clean solar panels also pose risks. Abrasive wear. Wind-blown dust acts like sandpaper. Over months and years, this abrasion scratches camera lenses, degrading image quality, wears down mechanical seals and moving parts, erodes paint and coatings, damages exposed sensors, structural stress. High winds create mechanical loads on solar panel arrays, which act like sails, catching wind, antennae and cameras on articulated mounts, rover masts and instrument booms, spacecraft body panels and attachment points. Dust infiltration. While dust devils can clean panels, they also stir up vast amounts of dust that infiltrates mechanical joints, causing increased friction and wear, electronics enclosures, potentially causing shorts or overheating, thermal systems, clogging vents and reducing heat dissipation. Curiosity and Perseverance. The newer rovers. Curiosity, 2012, and Perseverance, 2021, use nuclear power rather than solar panels, making them less dependent on cleaning events. But they still face erosion challenges. Curiosity's wheels have suffered significant damage from sharp rocks and rough terrain, but wind-driven abrasion has also contributed to wear. Engineers now see holes and tears in the aluminum wheels, some of which may be accelerated by wind-blown dust over the rover's 12-plus years of operation. InSight Lander. NASA's InSight Lander, 2018 to 2022, provides a cautionary tale about the risks of dust accumulation without sufficient cleaning. InSight relied on solar power, but landed in a region with less frequent dust devil activity. Over time, dust accumulated on its panels faster than cleaning events could remove it. Power levels dropped steadily. By late 2022, dust covered so much of the panels that InSight couldn't generate enough power to operate. The mission ended not because of mechanical failure, but because the lander starved for energy under layers of dust. The stronger winds discovered in Bickel's study suggest landing site selection should prioritize areas with frequent dust devil activity. For solar-powered missions, engineering margins for structural loads need to be increased. Materials selection should account for more aggressive, abrasive environments. Long-term missions, 5 to 10-plus years, face higher cumulative wear than previously modeled helicopters and drones. Mars helicopters like Ingenuity face unique wind challenges. Flight safety. Wind gusts can destabilize aircraft or push them off course. Ingenuity's flights were carefully planned around predicted weather, avoiding high wind periods. With baseline winds higher than expected, the operational envelope for future aircraft becomes more constrained. Acceptable wind speeds for takeoff-landing are lower than hoped. Flight paths need larger safety margins. Some days may be entirely unsuitable for flight dust damage. Helicopter blades spinning at 2,400 RPM in a dusty environment experience intense abrasive wear. Stronger winds mean more suspended dust, accelerating blade erosion. Engineering implications. Future robotic missions will need 1. Robust structural design. Components must withstand higher wind loads, with safety factors increased by 50–100%. 2. Improved dust protection. Better seals, filtered enclosures, and materials resistant to abrasive wear. 3. Active cleaning systems. Solar-powered missions may need mechanical wipers or vibrating panels to supplement wind cleaning. 4. Conservative landing sites. Avoid regions with extreme wind conditions unless mission goals specifically require them. 5. Accelerated testing. Ground testing should simulate the newly discovered wind speeds to validate designs before flight. If 160 km/h winds matter for robots, they're absolutely critical for human missions to Mars. The stakes escalate from equipment damage to astronaut safety. Habitat design requirements. Future Mars habitats, whether inflatable modules, 3D printed structures, or prefabricated rigid units, must withstand the full range of Martian wind conditions. Structural loading. With wind speeds reaching 160 km/h, habitats face significant aerodynamic loads. Pressure forces, direct wind pressure on walls, roofs, and airlocks. Suction forces. Low-pressure zones on the leeward side can literally try to pull structures apart. Vibrational loads. Fluctuating winds cause structures to vibrate, potentially leading to fatigue failure over time. Design considerations. 1. Shape and orientation. Streamlined designs reduce wind resistance. Habitats may need to be oriented with their smallest profile toward prevailing winds. 2. Foundation systems. Stronger winds require more robust anchoring. Deeper foundations or larger anchor plates. More anchor points per structure. Regular inspection and maintenance of anchors. 3. Material selection. Habitat. Materials must be strong enough to resist wind loads without excessive weight, resistant to abrasive wear from wind-blown dust, durable over decades of exposure. 4. Safety factors. Engineering designs include safety factors, margins above expected loads. The discovery of stronger winds means these safety factors must be larger, which increases mass and cost. Power system vulnerability. Solar power is the most practical energy source for early Mars missions, until small nuclear reactors can be deployed. But solar arrays are vulnerable to wind. Large solar arrays as wind sails. A typical Mars habitat might require 10-20 kilowatts of power, necessitating solar arrays covering hundreds of square meters. These arrays act like sails, catching wind and creating enormous forces on their mounting structures. At 160 km/h, a 100-meter solar array experiences forces equivalent to lifting several tons. Mounting structures must be massively overbuilt to prevent collapse. Array orientation systems must be robust enough to position panels in high winds, dust accumulation, and cleaning. For human missions, power is non-negotiable. Unlike rovers that can enter low-power hibernation, habitats must maintain life support continuously. Strategies include tilted arrays, mounting arrays at steep angles so dust slides off more easily, active cleaning, mechanical wipers, vibrating surfaces, or electrostatic dust repulsion systems, redundant capacity, building 30 to 50% more array area than minimally needed to account for dust-degraded efficiency. Backup power, battery systems or fuel cells to carry through dust storms when solar input drops, EVA, extravehicular activity. Safety astronauts working outside habitats face direct wind exposure. Suit design implications. 1. Stability. Astronauts in pressurized suits already have limited mobility. High winds could knock them over or push them off balance, risking suit breaches or injury. 2. Visibility. Dust storms and dust devil activity can reduce visibility to near zero, making navigation impossible and creating life-threatening disorientation. 3. Dust infiltration. Suit joints and seals must completely exclude Martian dust, which is fine, electrostatically charged, and potentially toxic. Stronger winds increase dust exposure during EVAs. Operational restrictions. NASA will likely establish EVA wind speed limits. No EVAs when sustained winds exceed 50-70 km/h. Immediate shelter protocols when dust devils are detected nearby. Mandatory buddy system with tether lines in moderate wind conditions. Designated storm shelters within short distances of any work area. Landing site selection. The stronger winds constrain where humans can safely land and establish bases. Favorable characteristics. Terrain with natural wind breaks, crater floors, valleys. Low dust devil frequency, based on historical observation. Stable weather patterns without extreme variability. Proximity to resources, water, ice, minerals, worth the wind risks. Unfavorable characteristics. Open plains with unobstructed wind flow. High elevation areas with more extreme temperature swings. Regions known for frequent dust storm formation. Areas with loose regolith that wind can easily mobilize mission risk modeling. Every Mars mission undergoes extensive risk analysis. Mission planners assess probability of various failure modes, consequences of those failures, mitigation strategies to reduce risk, wind-related risks, habitat breach due to structural failure, potentially catastrophic solar array damage, reducing power below life support requirements, critical astronaut injury during high-wind EVA, severe extended dust storm preventing EVAs for weeks. Significant operational impact. The discovery's impact. Bickle's study provides more accurate wind data. which reduces uncertainty. Mission planners can design for known conditions rather than guessing increases confidence. Better data means better predictions and more reliable safety margins. Raises costs. Designing for stronger winds requires more robust and expensive systems. Improves site selection. Identifying regions with more benign wind patterns becomes a top priority. The bottom line for human exploration. We can design for 160 km/h winds. We can build habitats that survive them. We can create protocols that keep astronauts safe. But it requires acknowledging reality. Mars is windier and more challenging than we thought, and engineering accordingly. Underestimating the wind isn't just an academic error. For future astronauts, it could be fatal. The discovery of Mars's true wind speeds isn't just about understanding the past, it's about predicting the future. Building a predictive framework. For decades, Mars weather prediction has been limited by sparse data. A handful of landers measuring conditions at fixed points. Orbital imaging providing snapshots, not continuous monitoring climate models based on incomplete understanding of atmospheric dynamics. Bickle's study represents a breakthrough, combining orbital observation with surface phenomena to create a statistical model of wind behavior. The integration approach. Step 1. Orbital monitoring. Current and future Mars orbiters can track dust devil formation and movement in real time, identify regions of active dust lifting, monitor dust storm development, provide early warning of approaching weather systems. Step 2. Surface measurements. Landers and rovers provide precise wind speed and direction at ground level, temperature, pressure, and humidity data. Local dust concentration measurements, correlation between orbital observations and surface conditions. Step 3. Statistical modeling. By combining decades of data, researchers can identify seasonal patterns, when and where winds are strongest, correlate wind speeds with time of day, location, and topography, predict dust devil frequency for any given region, estimate maximum expected wind speeds for mission planning. Step 4. Machine learning. Enhancement. AI algorithms can detect complex patterns humans might miss, generate probabilistic forecasts, e.g. 70% chance of winds, 100 km/h tomorrow, continuously improve predictions as more data arrives, provide real-time alerts for high wind events, real-time weather monitoring. Future Mars missions will benefit from something we take for granted on Earth: weather forecasting. The vision. Within 10 to 15 years, Mars could have multiple orbiters with dedicated weather instruments continuously monitoring atmospheric conditions, a network of surface weather stations deployed across key regions by rovers and landers, AI-driven prediction systems providing 1 to 7 day forecasts for wind, to temperature and dust activity, alert systems warning missions of incoming dust storms or extreme wind events. Practical benefits. For robotic missions, plan flights and EVAs during optimal weather windows, prepare for dust storms by securing equipment and entering safe modes, optimize power management by predicting solar panel cleaning events, select traverses that avoid high wind regions. For human missions, schedule EVAs when conditions are safest, prepare shelters before major weather events, manage resources, power, water, oxygen, based on predicted conditions, coordinate activities across multiple habitats, knowing what weather to expect. One immediate application: using the new wind data to refine landing site selection for upcoming missions. Mars sample return, 2030s. NASA and ESA's plan to retrieve samples collected by Perseverance requires landing a rocket, the Mars Ascent vehicle, that will launch samples to orbit, This rocket must survive Martian weather between landing and launch, potentially months. Landing sites can now be evaluated for wind risk using Bickle's methodology, Human Landing Sites, 2030s-2040s. NASA's Artemis to Mars program will eventually require selecting sites for crewed landings. Wind is now a top-level selection criterion. Site A. Scientifically interesting but high wind exposure. Site B. Moderately interesting but sheltered location with low wind risk. The balance between science goals and safety shifts. When we know winds can reach 160 km/h, beyond practical mission applications, the improved understanding of Martian winds advances fundamental science. 1. Atmospheric circulation models. Climate scientists can refine global circulation models, improving predictions of seasonal weather patterns, dust storm initiation and evolution, long-term climate trends. 2. Dust cycle studies. Understanding how dust moves through the atmosphere helps explain why Mars looks reddish-orange. Dust in the air scatters red light. How dust affects surface temperatures. The role of dust in Mars's ancient climate when the atmosphere was thicker. 3. Geological evolution. Better wind models help geologists interpret ancient sedimentary deposits, erosion patterns suggesting past climate conditions, the history of Mars's atmosphere over billions of years. 4. Comparative planetology. Lessons from Mars apply to other dusty worlds, like Saturn's moon Titan. Understanding how thin atmospheres behave, predicting conditions on exoplanets. With similar characteristics, Bickle's study exemplifies how modern planetary science works, combining massive datasets, AI analysis, and international collaboration to answer fundamental questions. Mars winds regularly reach 160 km/h, far stronger than previously believed. Dust devils are common, powerful, and critical to Mars's climate system. Geological features like dunes and erosion patterns are explained by normal wind activity, not rare events. Robotic missions face increased abrasion and structural risks, but benefit from solar panel cleaning. Human missions require more robust engineering with higher safety margins. Future exploration will integrate orbital and surface data to predict weather and reduce risk. For decades, we viewed Mars as a cold, dead world, with a whisper of atmosphere barely capable of moving dust. The reality? Mars is dynamic, powerful, and constantly reshaping itself. The winds we discovered aren't anomalies, they're normal. Mars isn't quiet, it roars. And if we're going to visit, explore, and eventually live there, we need to respect that power and design accordingly. As we stand on the threshold of a new era of Mars exploration, with sample return missions launching in the 2030s and human missions following shortly after, the discovery of Mars's true wind speeds represents a crucial correction to our understanding. Somewhere on the red plains of Mars, dust devils are spinning right now. They tower kilometers into the thin atmosphere, their winds approaching hurricane force, scouring the surface and lifting dust that will circle the planet for months. They're beautiful. They're powerful. They're everywhere. And thanks to Valentin Bickle's team and the thousands of images captured by orbiting spacecraft, we finally understand them. Mars isn't the gentle, quiet desert we imagined. It's a world of extremes, and its winds are more extreme than anyone expected. But extreme doesn't mean impossible. It just means we need to be smarter, more careful, and better prepared. Because we're going to Mars, and when we get there, we'll be ready for the winds that await us.